Study Unit 5, Lecture 5. This lecture carries on with looking at how transformers influence the core MMF imbalance which can be present in transformers, specifically in three-phase systems, in half-wave and full-wave rectifiers. So a three-phase transformer will also consist of a set of primary coils and a set of secondary coils, and these coils can have a combination of either a star or Y configuration or a delta configuration. Probably the most obvious difference between the two is that with the star or Y configuration there is a neutral path out of the center of the transformer. The general convention when referring to the configuration of the transformer is to cite the configuration of the primary coil followed by the configuration of the secondary coil. So for a YY transformer which has a Y primary coil and a Y secondary coil, that transformer will be designated by a capital Y for the primary coil and a lowercase y for the secondary coil. So using the same convention, there can be Y delta coils, there can be delta Y coils, there can be delta delta coils. These different combinations are used because certain voltage and current characteristics may be desired in the transformer. So a Y configuration will reduce the winding voltage by √3, whereas a delta configuration will reduce the winding current by √3. So for example, a YY configuration might be necessary when two neutrals are required for grounding purposes, although a problem with the YY configuration is that there will be triple N currents which flow through the neutral and need to be minimized by designing a beefier neutral terminal. Delta Y configurations are useful for step-down voltage applications. The delta-delta configuration finds application in medium-high voltage applications where no neutral terminal is required. Last but not least, delta-Y configurations are used in step-up applications. So independent of whether it's a delta-Y or Y-delta or whatever other possible combination there will be, the power rating or the apparent power of the transformers given, of those transformers are given by this equation here, which is √3 times the voltage on the line multiplied by the current in line. So that means 3 times the voltage of each phase multiplied by the current in each phase. Also, for both the primary and the secondary voltages, the total voltage will be 0. In other words, if the voltage between each phase is taken and added together, the total will be 0. So as an example shown here is a Y delta transformer. So the ratio for this transformer is given by the number of primary coils divided by the number of secondary coils. So multiple relationships between the primary and secondary coils can be used to describe this ratio. For example, the voltage from terminal A of the primary to neutral will have the same ratio to the voltage between terminals A and B on the delta or secondary coil as the number of primary to secondary coils for both transformers. The voltage between terminals A and B of the primary coil is the voltage between A and neutral, subtracted from the voltage between B and neutral, which is equal to the voltage between A and neutral minus the phase shifted version of the input signal at terminal B. So this will be the same voltage at terminal A and neutral, except it is now phase shifted by 120 degrees, which can be rewritten as √3 multiplied by the voltage at terminal A shifted by 30 degrees. In the same way, the current in terminal A of the secondary can be expressed in terms of the other currents. Finally, in a delta configuration, the total current flowing through the transformer will be 0. So current A and B and C will cumulatively be 0. Lastly, the output current rating will be the power rating of the transformer divided by 3 times the maximum input voltage. A similar family of relationships between the different characteristics of the two coils can be written down for all combinations of Y and delta transformers. So a good way to compare these transformers is to look at the output current rating. So shown here, depending on the type of configuration, the output rating for the transformer pairs will be different. So YY, delta and delta Y all have a similar output rating of absolute value of S over √3V. A Y delta transformer pair has an output current rating of absolute value of S divided by 3V. Shown here are two half-wave rectifiers, one using a YY configuration and one using a delta Y configuration. Both these examples do not have a delta in the secondary, and this is because a delta cannot be used for a half-wave rectifier. This is because there is no neutral terminal on a delta transformer coil. The absence of a neutral terminal means that there is no return path for the currents which are induced in the secondary coil from the primary during half-wave rectification. In the YY configuration, each primary-secondary pair of the three will share the MMF0. So MMF0 can be given by the number of secondary terms multiplied by the current in the secondary minus the number of primary terms multiplied by the current in the primary. And this type of expression can be written down for each of the three arms of the star. So using this MMF0 expression as well as the expression for the sum of the currents, the net DC bias MMF can be calculated. Star configuration, there is a neutral terminal at the center of the star, and the currents flowing into the terminal must be equal to 0. So all the currents will additively equal to 0, meaning IP1 plus IP2 plus IP3 equals 0. So just for example, current IP1 will be equal to the number of secondary terms divided by the number of primary terms multiplied by ratios of each of the currents in the secondary coil. Similar expressions can also be written for IP2 and IP3, and if this is then back substituted into the MMF0 expression, a total for the DC MMF bias can be determined. So for a YY configuration, the MMF DC bias is equal to 1/3 multiplied by the number of secondary turns multiplied by the output current. A similar approach can be used to determine what the MMF DC bias will be for the delta Y configuration, but it will be found that the MMF0 for the delta Y configuration is the same as that for a YY configuration. In other words, neither of these configurations is able to deliver a 0 DC MMF bias. The difference in topology does not have an effect on the DC MMF bias, but does have an effect on the analog behavior within the coils, even though the net DC MMF bias is the same. Shown in this diagram are once again two different transformer types, and these are two examples of three-phase transformers which make use of hexaphase rectification. In both cases, the secondary consists of a dual Y configuration, but example A has a Y primary and example B has a delta primary. So what's interesting about this configuration is that the DC MMF bias is now determined by the primary, whereas in the previous examples it was determined by the secondary. So the MMF can be derived in a similar fashion to the previous example. There are these balanced MMF relationships which define how the secondary currents and number of turns relate to each other. Also, because of the star configuration in the primary, all the currents flowing into the center of the star need to add up to 0. This IP1 just expresses the current in one of the arms of the star and is given as the ratio of the secondary turns to the primary terms multiplied by the ratio of the other currents in the coil. Substituting back in allows MMF0 to be given as number of secondary terms divided by 3 because there are 3 arms, divided by these pairs of differences between the currents in the secondary. What all this really means is that for this type of configuration there is no DC MMF bias, but there is a periodic change in the DC MMF bias when compared to the previous examples which had a constant DC MMF bias. So for this transformer configuration here, even though there is no constant DC MMF bias, there is a periodic behavior in the MMF. The delta YY configuration does not have this alternating DC MMF, but the problem with a delta configuration is that triple N currents can flow in the transformer coil or the primary. So it can be seen with this previous picture which shows the old half-wave delta Y rectifier is that the delta Y rectifier had a DC bias, but with the introduction of a secondary Y transformer, this MMF0 DC bias can be removed. In both cases, where there is the Y and then the two secondary white transformers and with the primary delta of the two secondary white transformers, there are some tricks that can be done to remove the DC MMF bias. For the examples which you made use of the half-wave rectifier, a zigzagging technique in the transformer coils was used to reduce the DC MMF, and this zigzagging method can also be applied to the full wave rectification for three-phase systems over here. Shown here is a wire arrangement or star arrangement transformer coil which has a secondary turn on each arm of the coil. In this configuration there is a balance in the MMF and currents between adjacent branches. So using this balance configuration, it means that the net DC MMF will be 0 in a star and star-star configuration. And that concludes this lecture. The final lecture for the study unit will have a look at voltage multipliers. The different transformer configurations which were discussed in this lecture all differ in the configuration of the primary and secondary and how this influences the DC MMF bias. The student is encouraged to use the reference text to look at the derivation of these waveforms which describe the analog behavior in each of these transformer sets. And this concludes this lecture.